we're now going to use gravitational attraction, so the force of gravitational attraction, to determine little g. And just a refresher, little g is the acceleration due to gravity. It's also the gravitational field strength. In other words, little g will change depending on where you are. It has to do with how attracted you are to the object you're on. So for example, Earth, the moon, any other planet, a star. So we're going to look at how to use Newton's law of universal gravitation to determine g, and then I'll do an example. So again, just to refresh, g is the acceleration due to gravity. We can also refer to it as the gravitational field strength. And all that means is how much the object is pulling down on you. So gravitational field strength. On Earth, we use the value of g to be about 9.8 meters per second squared. And that's assuming that you're at the surface of the Earth, but it changes depending on where you are. So as soon as you leave the surface, that gravitational field strength is going to start decreasing a little bit. We know that any two objects are attracted to each other using the equation F big G equals G m1 m2 over r squared, where r is the distance between the two objects. We also know that whenever you're on a massive object, you're going to be attracted by its gravity. So the gravitational attraction is equal to the force of gravity, or the weight. This weight will change as the distance between the centers of the two objects changes. So that's why g equals 9.8 meters per second squared is only valid for when you're on the surface of the Earth. And again, this will change as you leave the surface of the Earth. So let's derive g on the surface. G m1 m2 over r squared is equal to mg. So this is just saying that Fg equals Fg. The mass over here is the mass of the object. So let's say you're doing this for you. And let's say your mass equals 70 kilograms. So G m1 m2 over r squared, we'll just make this m1. So this is the mass of you, mass of you, mass of the second object, in this case the Earth, and the distance between the two. You'll notice that your mass is irrelevant. It appears on both sides. So we are left with G m2 over r squared equaling little g. So on Earth, you're dealing with your mass 2, in this case is the mass of Earth, so big M, and the radius of the Earth since you're standing at the surface. So this will be our big R. And again, I'm using big M and big R because those are already stored in your calculator. So G on the surface of the Earth should equal big G times the mass of the Earth divided by the radius of the Earth squared. So putting that into your calculator, I have G M divided by R squared, and I get 9.8034, keeps on going, meters per second squared equaling G. So G is about equal to 9.8 meters per second squared. Look at that magic. Let's figure out what G is on the moon. So moon. G times the mass of the moon over the radius of the moon, so I'll just put a little m squared, will give me the gravitational acceleration on the moon. Mass of the moon is equal to 7.3 times 10 to the 22nd kilograms, and the radius of the moon is equal to 1.7 times 10 to the third, times 10 to the 6th, not third, 10 to the 6th meters. So using these numbers, for the moon we're going to put in G and then 7.3 times 10 to the 22nd kilograms over 1.7 times 10 to the 6th meters squared equaling G. And we get 1.68, keeps on going, meters per second squared equal to little g on the moon. So little g on the moon is about 1.7 meters per second squared. A lot of times you'll see it's about 1.6, that's just from rounding, so I could have made these a little bit longer in terms of their decimals and we would have gotten something a little bit closer to 1.6. But in general, anytime you're looking for the gravitational acceleration, or little g, on another planet, it's going to be equal to big G, which is the same everywhere in the universe, times the mass of that planet or moon divided by the radius squared. So m is the mass of the object, and this is your large object, so planet, moon, star, something like that. And this is the distance between the centers. So I say distance between the centers. The two examples I did was the surface gravity. Let's look and see if we're not on the surface. Okay, so let's see what the acceleration due to gravity is on a mountain 10,000 meters above the surface of the Earth. Our given information, we know that the mass is equal to the mass of the Earth. We know that the radius is equal to the radius of the Earth plus 10,000 meters. And we're looking for g at that height. So little g equals gm over r squared. So this equals g times the mass of the Earth over the radius of the Earth plus 10,000 meters squared. So putting this into our calculators, we're just going to do gm. So again, if you store these, your life's a lot easier. Gm divided by the radius of the Earth, and this whole quantity needs to be squared, plus 10,000 meters squared. G equals 9.772, keeps on going, meters per second squared. So the acceleration due to gravity on a mountain 10,000 meters above the Earth, I only put one sig fig here, it's approximately equal to 10 meters per second squared. But notice that this number, 9.77, is less than 9.8. So the farther away you are from the surface, the less amount of gravity you're going to have. So that's how we can determine little g on any object in the universe. And again, by objects, I mean planets, moons, or stars. All you're doing is looking at the mass of the object and the distance from the center. So how far away from the center of the object you are. And then you can find g.